Thank you, Claudio, and thanks very much for the invitation and this opportunity to present the work we've been doing with my group in Banda. Seismic tomography has given us increasingly detailed images of distributions of seismic velocities in the mantle and in the crust. From those, especially in the mantle, we can infer distributions of temperature, and by inference, lithospheric thickness, lithospheric strength, all these useful parameters for if we want to study lithospheric dynamics. Another useful observable is seismic anisotropy, directional dependence of seismic wave speeds, and that gives us a proxy of deformation and flow in the lithosphere and asthenosphere. This can be either present flow if there is active flow or flow in the past. When we study lithospheric dynamics in evolution and related to evolution of topography, we are trying to sample a four-dimensional space of space and time. And our sampling of this space with data is always very sparse. So we would like to get as much evidence as we can from different fields. So seismic tomography can give us isotropic average seismic velocities, and that's temperature and thermal structure today, now. And anisotropy can give us proxies for flow either now in the asthenosphere or currently deforming crust or mantle lithosphere, or in the past, currently stable crust or mantle lithosphere will contain frozen fabric that's formed during the last major deformation episode. To that, we can add geodesy, which gives us surface deformation. Today, geological record gives us incomplete but valuable samples of how the crust deformed in the past, and we can try to reconstruct what happened. This is our current model with Andrew Schaefer. This is a sliding horizontal cross-section that's going from top of the mantle to middle of the upper mantle, and it shows nicely the workings of plate tectonics from mid-ocean ridges where oceanic plates form, then they cool and subducted trenches, and continental lithosphere contains very fast, thick, cold cratons and distinctly different tectonic parts. So we can, the way we do it is with waveform tomography, and if we use sufficiently wide frequency range, we can resolve continental crust, where the highest anomalies we see here is Tibet, very low velocities. And when we look to mantle lithosphere, the cratons stand out as the most anomalous locations. And now, a perspective plate tectonics, Azimuthal Anisotropy, we can see it very clearly. If we look at the Pacific plate, in the asthenosphere, the fast directions that characterize the current shear in the asthenosphere are parallel plate motion. And in the lithosphere, the fabric is frozen. And so the fast directions are parallel to paleo-spreading directions. So this is when the lithosphere formed. This is what the shearing was like. We've been collaborating with Thorsten Becker recently on combining this type of data with geodynamic models, and Thorsten found very interesting patterns that tell us about the mechanical boundary between the lithosphere and asthenosphere and how it deepens with age. But in this talk, I would like to focus more on regions where plate tectonics breaks, that is, deforming continental lithosphere. So the two parts of the world I'm going to focus on is Tuscany in the central Mediterranean, and then the India-Asia collision zone and Tibet. In Tuscany, this famous landscape is formed by deformation of the lithosphere that has been stretched by a retreating trench. This slab that has been rolling back is, in tomography, it comes out as this continuous feature, which tells us that production of the same slab continues for some tens of millions of years. and we are just above this slab here. The morphology of the subducting slabs is quite complex, so we are somewhere here on top of this slab. And thanks to that, there will be very complex mantle flow in the asthenosphere. The asthenosphere will be pulled by the retreating Calabrian trench, so probably there will be flow in the asthenosphere associated with that. But all this complexity will make other patterns as well. So this is the observables we have from seismology, shear wave splitting, which tells us about flow and deformation in the asthenosphere. And indeed, we see this northwest-southeast flow below Tuscany towards Calabria. Now, indicators for crustal flow, geodesy tells us what the extension is today. And metamorphic rocks show lineations that tell us about the extension in the last few million years. And this extension is approximately east-west. Now, an interesting question about Tuscany, about its lithosphere, is first of all, is there any lithosphere? And by that I mean mantle lithosphere. If you make this piece of new crust by stacking blocks of continental crust during the continuous subduction of mantle lithosphere, what happens inevitably that mantle lithosphere from the crust, and the new crust that you form and deform does not have any mantle lithosphere attached to it. And this consideration motivated this model that says that there isn't indeed any mantle lithosphere below Tuscany. And some tomography was interpreted as supporting that, showing low P velocities below the Moho in Tuscany. So that would be very different from normal conventional models of continental lithosphere, which has crust and below a layer of mantle lithosphere. So we've done tomography of this, seismic imaging of this region using a few stations of retreat array. Have measured phase velocities of Love and Rayleigh waves, and those we can invert for S-velocity profiles. So this is the average over the region dispersion curves for Love and Rayleigh waves, and we can invert those for these profiles of S-velocities. All these models fit equally well, so we're looking at a suite of models rather than one, but they show consistent features, and here I interpret them with labels. So first of all, at 150 kilometer depth and below, there is a big anomaly with respect to global average. That's the subducting slab, we know that. But if you look at shallow mantle, the data requires a high velocity layer on top of a decrease of a low velocity zone. So that would be characteristic of a lithosphere. Colder layer, higher velocities, and then lower velocity zone below. We can also look at anisotropy. The difference in seismic velocities in different directions as a function of azimuth, we can fit best fitting fast propagation directions to it. And although there is noise in the data, there is a very consistent pattern of fast directions at short and intermediate periods that sample upper crust, lower crust, and uppermost mantle. And then there is a sudden change to a different direction. So the summary of those patterns is there is east-west fast direction at short periods that sample the crust and uppermost, and it's the same direction at all these periods, and it coincides with the direction of recent extension. And then once we go to deeper mantle, there is a different direction, apparently asthenospheric, which coincides with measured by shear wave splitting. So what we resolve with the two types of measurements is continental crust and lithospheric mantle, apparently, that deform in the same way and in the same way as the deformation at the surface, which we see from other types of measurements. And then below a lithosphere-asthenosphere boundary, about 60-70 kilometer depth, the pattern of deformation changes to a stenospheric one. The stenospheric, so we understand what happens in the lithosphere. There is stretching. What drives the flow in the asthenosphere? The retreat of Calabrian slab is one strong candidate, but it's going to be a very complex flow in such a complex part of the mantle. So these two lines of evidence both show us that there is likely to be a mantle lithosphere that is very young, possibly youngest, some of the youngest in Europe. We know that the crustal blocks lost their mantle lithosphere very recently, but the mantle lithosphere grew in the last 10 million years or so. And in fact, thermomechanical models show us that it's very difficult to prevent lithosphere from growing rather quickly. There will be, it will, to completely equilibrate it, of course it takes time, but to maintain a situation with no mantle lithosphere is very difficult. It will grow by a few tens of kilometers very quickly. So this is apparently what in Tuscany. And the influence on topography of both the stretching of the crust and the growth of mantle lithosphere will be subsidence. Now, moving to India-Asia convergence zone, Tibet shows an even more spectacular topography. And the origin of this topography is debated and has been related to processes in the mantle and flow in the crust. One of the proposed models for lithospheric convergence invokes convective removal of lithosphere beneath central and eastern Tibet, which would cause the uplift of this part of the plateau. And an alternative model suggests that the channel flow in the crust may have contributed to growth in the thickness of the crust in the east, and therefore the uplift. So these are some of the mechanisms of convergence that are advocated today. There is underthrusting, either the entire plateau or parts of it. There is viscous thickening with stabilization of the thick lithosphere, thickening followed by drips or convective removal of lithosphere, and different flavors of subduction, shallow angle, steep angle. So what happened is that India hit Asia at some point in the past. At the moment it's debated how long ago that was, and that's related to the size of Greater India, the part of India that has been consumed in the collision. Recently, a few models were proposed by different groups suggesting that Greater India was in fact much narrower, which implies differences in plate tectonic, how plate tectonic works in the Indian Ocean in the past. So what does tomography tell us? Very low velocity crust, as we've seen, and then heterogeneous upper mantle with complex anomalies that change at different depths. If we slice through it, in the west, there is what appears to be underthrusting of continuous Indian lithosphere all the way up to Tarim, the stable part of Asia. And as we go towards the center, very shallow angle subduction we can see. And in the east, there is also continuous anomaly of apparently Indian lithosphere, also showing very shallow angle subduction. If we look at with different type of data with array measurements trying to pinpoint exact amplitude of anomalies, the amplitude is, this lithosphere is very cold because this Cloetingh lithosphere recently underthrust under the Tibetan crust, and therefore pushed down into the mantle. So that's why it is, in fact, the fastest anomaly on the map, much faster than normal cratons. So the size of Greater India that we can map with, from a tomographic image matches very closely with recent reconstructions for this smaller Greater India. It does not resolve the debate completely by itself, but at least it shows that this much of then subducted at shallow angle beneath Tibet at present. and there are complexities and across the Himalayas in the way India is consumed from underthrusting in the west to underthrusting and subduction in the central part and shallow subduction in the east. Now, if we focus now on Tibetan crust, it shows very low seismic velocities. So in the middle crust shows velocity zone in the northern part of Tibet with decrease below about 20 kilometers. And in the southern part, there is not such low velocity. Nevertheless, it's very slow. So that's another way to plot it. Low velocities in the south and very low velocity in the north. And even conservative estimates give substantial melting that should correspond to such low velocities. So what this implies is that the viscosity is likely to be very low in these rocks. So there are conditions for channel flow. This has been a provocative model. However, it is accepted by many people in our community. And at least to some extent, channel flow is expected to happen. So what happens according to this model is that gravitational spreading of the plateau is the basic driver of the deformation, and the viscous middle crustal material is squeezed out between the rigid cratons towards the southeast and northeast. And we can test that with direct measurements of flow, if we can make those. So we've tried to do that with anisotropy, and in the middle crust, the fast directions in the central part of the plateau are east-west, which is parallel to the current motion at the surface. And then at the northeastern part of the plateau, the fast directions are northwest-southeast. And when we look in the mantle, probably in the asthenosphere, the direction is different and now is parallel to the plate convergence direction. So what this tells us, so here we try to integrate a few different observations. So these arrows are the strain rate at the surface, and the extension component of the strain rate field is east-west in central Tibet. And what we see at depth within the crust is that the deformation is exactly the same as at the surface. Fast direction parallels extension at the surface. And the same thing happens northeastern, that the fast direction, or probably extension, by inference parallels the extension at the surface. So what this tells us is that even though we know that viscosity in the middle crust is very low and there are conditions for channel flow, nevertheless, channel flow implies that deformation within the channel is different from that above and below. Here we see exactly the same deformation throughout Tibetan crust. And then it changes to something different in the asthenosphere. So this suggests that even though conditions may exist and probably some flow within the crust does happen, but the dominant pattern of deformation is not channel flow, but deformation throughout the entire crustal thickness. So that's all I wanted to show. Thanks.
Questions? Sì. Thorsten.
Sergei, is that contingent on the flow in the crust forming some sort of fabric that has the fast axes aligned with the shear you expect?
Yes.
And I mean, do we know that?
That's a very good question. We don't know why that is, but empirical evidence show in any origin you look at, and wherever you compare different indicators of flow and deformation, crust behaves as though it was made of olivine, and by that I mean as though it was a single mineral that shows fast direction in the direction of extension. In the crust, there are many minerals with different types of anisotropy, and they can be expected to behave differently. But empirically, crust does behave as though it was made of olivine. It shows fast direction in the direction of extension. For example, if you look at Tuscany, and there are many examples like this, we see exactly the same anisotropy in the mantle lithosphere and in the crust. It's very unlikely to be a coincidence there and everywhere else. Does that answer your question? But it's an open question what exactly happens. There are many anisotropic minerals in the crust, and why it works like this, I'm not sure we know.
Okay. Yeah, that's a very interesting point. Any other? See, Hitoshi.
Okay, this is more technical question, but for the separation of azimuthal anisotropy in the crust and lithosphere and here crust and astenosphere, I guess. You assume some sharp cutoff. I mean, you cannot directly resolve from your surface waves observation alone, right?
Why not?
How? I mean, gradually change the frequency, right?
Well, just like we invert, I don't have the technical plots here, but just like we invert surface wave dispersion curves for isotropic profile or for radial anisotropic profile, we can invert it for azimuthal anisotropic profile.
Sure, but you assume some depth, like lithosphere and astenosphere or the crust and astenosphere, sharp cutoff. Is that? Or you continuously solve for depth profile? Or?
Yes.
Oh, okay.
For Tuscany, we didn't do that. There it was very obvious that there was one parting and then the other. But for Tibet, actually, we did plots which we did inversions which I don't have here, but we can obviously invert for an anisotropy profile just like isotropic one.
Okay. So any other question, comments? So when you do sum up the two contributions, what would be on the surface the result actually? So the mantle will dominate over the crust or not?
You mean if you split the shear wave?
Right.
Oh, sorry. Oh, here it is. Yes, that's a good question. So in Tibet, shear wave splitting is very funny. There is some consistent inconsistency, as we could define it. There are, at the same places, different measurements. And so overall, there is, if you look from a distance, there is consistent pattern. But if you look at points, there are measurements that are in different directions consistently. And this is what we predict from anisotropy that we resolve for shear wave splitting. It's a very simple-minded computation. We just take one layer and then the other layer separately, and not propagate waves through the entire thing like Torsten would do, which we should try, of course. But so the mantle would give us this much, and crust would give us this much. And depending on the azimuth of the shear wave where it comes from, these will combine in some way that's not entirely intuitive. But it appears that these ones are parallel to the crust, so it appears that at least these measurements, given S waves that were used, were dominated by the crustal pattern.
That's very interesting. Any other comment? Okay, Riske?
Yeah, Sergei, nice talk. I had a question about this dominance or non-dominance of channel flow. I mean, you conclude that since the anisotropy in the crust, both in the middle crust and the upper crust, is the same, that channel flow cannot be the dominant. But if you can also turn it around and say that the upper crust is actually slave to what's happening in the middle crust, and then argue that channel flow is actually quite important and even drives deformation in the upper crust. Or
I guess it's just what's the definition of channel flow? I think the fact that middle crust is weak and is able to flow is very important in the dynamics of the plateau. That's why it can spread so efficiently. no question about that. But the channel flow is, people often understand it in the sense that the upper crust does one thing and the middle crust does something completely different. It just flows out. For example, in the northeast of the plateau, we know that it's compressed north-south and extended east-west, whereas channel flow is predicted to flow towards northeast. So that we can test with the data. And what comes out shows that deformation regime in the middle crust, the dominant regime that we can see, is the same as at the surface.
But I think, I mean, I'm not a channel flow I don't know, defending. I'm not defending this by per se, but I mean, I think the prediction from the people testing this channel flow hypothesis is that it would actually flow towards the east, or at least in an east-west direction. And the deformation that we see in the upper crust is east-west extension. And so that actually could be related.
The model in this end-member purest form predicts that the topography gradient will drive the flow. The flow will be parallel to topography gradients because the gravity is the driver. So it must flow in that direction. And like in Tuscany, if that happened, we would see past directions indicating flow towards northeast. And that would be the opposite of extension direction at the surface perpendicular to it. So this is where we can test it. And what we find out is that flow is not likely to be in that direction, but the pattern of deformation is predominantly as at the surface.
Yes, and for the case of Tuscany, I mean, I think it's your data is really relevant in the sense that also the prediction done by modeling show that the mantle is parallel, trench parallel moving, and the crust is orthogonal, as we can see on the surface as well. So it's really important. So thank you so much, Sergei. I think we have to move to the next talk.